We are live, so let's get started. So we were possibly the last lecture in the spectral methods module. We'll conclude our discussion on the Cheeger inequalities and then talk about expander graphs. So what were the Cheeger inequalities? So just let's do a quick recap from last time. So one second. Default. We were in the from last time. Doing the Cheeger inequalities. And what were the Cheeger inequalities? The Cheeger inequalities were these in which we are bounding the conductance of a graph. We're both upper and lower bounding. We're saying the upper bounded by 2 lambda 2, lower bounded by lambda 2 by 2, where lambda 2 is the second eigenvalue of the reversible random walk matrix of the Laplacian of the random walk matrix, and phi g defined as min of ps is the conductance of the graph, min over all s, such that 0 less than such that 0 less than pi of s less than or equal to half, conductance of a graph. And Ps itself was defined as the set of edges that go from S to it's the boundary by pi of S. This is how we defined one. These were what we had called the Cheeger inequalities. And we had proved one direction. The first inequality we had proved, that's called the easy direction. And what we are left with today is what is called the hard direction of Cheeger. The hard direction phi g is less than or equal to 2 lambda 2. Okay. So what is this sort of this direction telling you? That is, if the Laplacian has a small second eigenvalue, then the graph has a cut with a small conductance. And as we saw last time, we'll actually give as we mentioned last time, we'll actually give a constructive proof of the statement. We were going to show, we will prove this, we'll give a constructive proof. I'm just recalling several things that we did last time. The constructive proof along the following lines. What do I mean by constructive proof? So given a function on the vertices, this could be the second eigenvector. Such that two properties are true. One, f is orthogonal to the all ones and f is non-zero. By orthogonal, it's in the pi inner product. And two, the corresponding Rayleigh coefficient for f is small In particular, it is, if it was a second eigenvalue, it would be small. So if given something like this, LF phi FF phi says rho, then suppose F satisfies this, will construct a set S of vertices. So that firstly pi of S is less than or equal to half, and satisfying P of S is less than or equal to square root rho 2 minus rho if rho is less than or equal to 1, and 1 if rho is greater than. Okay. So you see that this will suffice to prove the statement of the lemma, whatever we had proved. This was where we were last time. Any questions so far? So this is what we will do. You give me a vector which has small, which witnesses the fact that the second eigenvalue is small. In particular, it's a vector orthogonal to the all ones, and its corresponding Rayleigh coefficient is rho. So in particular, the second eigenvalue is even smaller than rho. Then I will give you a cut whose conductance is small. This is going to be the outline of the argument. And we had further said the way we will be proving this is along the following lines. We will use something called a proper function. We said that G from V to R is a proper function. If the following is satisfied: 1, G of I is greater than or equal to 0 for all I in B. G is a non-negative function. And furthermore, the amount of weight it puts on the positive guys is not too large. Phi of I such that Gi is greater than 0. This is less than half. So more than half the guys, it actually puts a 0 value. This is what we had defined to be what we called proper. And we wanted to prove 2 lemmas. Let's prove them one after another. The first lemma will state that given our hypothesis, so given F, given non-zero F, from V to R, such that once again, F is orthogonal to the all ones function. So F1 pi, the pi is 0, and 2, say rho is the Rayleigh coefficient of F. Then there exists a non-zero proper G from V to R, such that the Rayleigh coefficient corresponding to G is small. Notice that G need not be orthogonal to the all ones function. The only thing about G is the fact that it is a proper function. And in particular, it cannot be orthogonal because anything that is orthogonal should have positive and negative guys. This has only non-negative guys, so it can't be this one. And how would one go about proving this? To claim the proof of this is actually fairly simple. We are just going to define G as following. Define G of I to be equal to f of I if f of I is greater than or equal to 0 and is 0 otherwise. I had to do one catch before this. I should have done that beforehand itself. So let us assume that's without loss of generality, we can assume that pi of set of all I, fi is greater than or equal to 0, is less than or equal to, is less than half. If not, replace f with minus f and then continue. Because if, for example, for the hypothesis of this lemma 1, whether you give f or minus f, they both satisfy the same property. Okay. And now we define G this way. So G certainly has the following. So G is proper. G is proper. Why? Because one is G is non-negative. That's clear. And G on, and clearly pi of I, Gi greater than 0. This is exactly the places where fi was greater than 0. So this is less than half. So G is perfect. Now, what we now need to understand is the Rayleigh coefficient corresponding to G. We want to show how is G LG pi right, compared to F. What we'll show is actually this is a summation, and term by term things drop. So let's actually look at S, which is set of all I such that Gi is greater than 0. This is the same as set of all I such that Fi is greater than 0. Now let's look at for I in S. Let's look at what is L of G. L of G of I. We saw last time itself, this is exactly Wij, Ij, Gi minus Gj over all J. This was the Laplacian, the definition of the Laplacian matrix had this property. This is what we saw from last time. Now, I want to claim this is, I want to replace G's with F's now. Because I is in S, Gi is the same as Fi. So this here I can replace this with Fi. What about Gj? Minus Gj is only going to become larger. Either it is Fj itself or it is going to become a larger quantity. So as an inequality, this is true. Term by term, this is each term is true, but this is exactly Lg. This is exactly Lf of I, which we know is here I'm using its lambda 2 Fi. Okay, I have to change the proof a little bit. So what I want to say is the following. This is lambda 2 of G. Do I need to do this? 1 second. Let's look at the proof. Now let's look at G LG. Right. Let me skip this particular step. Let's leave it as this. Let's look at GLG5. What is this? This is exactly, you only have to go over the non-zero quantity. So it's I in S, pi I, GI, LG of I. What is this? This is summation I in S, pi I. This is the same as Fi, and this is LFI. It's less than or equal to F. No. This proof, the way I stated the proof is wrong. So given non-zero F, and this happens to be the eigenvector. So I'm going to change this. Lambda 2, given non-zero second eigenvector. The F, I want it to be the second eigenvector, not any arbitrary function. I take F to be this. This proof can be modified, but the proof I have written over here is this. So because F is a second eigenvector, this is actually equal to lambda 2 Fi, which is the same as lambda 2 Gi. And this is exactly, here I could have directly gone. Here I didn't have written this. I could have written this as this is less than or equal to I in S, pi I, Gi, lambda 2 Gi, which notice is just lambda 2 times Gg. And hence we have our statement. Should have kept this as less than or equal to lambda 2. I think the previous statement I wrote is also right, but the proof which I have written down, it doesn't. It proves only for if F were the second eigenvector. Okay, are people with me so far? Okay, so now I'll prove the second, this one, lemma 2, if the following lemma, which we had stated without proof last time. If G is proper, with a proper non-zero function, then phi of G is less than or equal to square root rho 2 minus rho, where rho is the corresponding. Okay. So G is proper. So the way I'm going to prove this, G is proper. So we need to show this. We need to show this inequality. What we'll show is we will consider a nice enough term, and we'll upper bound it by this quantity and lower bound it by this quantity. Somehow the proof will go along this one. And which quantity will we look at? Let's look at G being proper. So if G is proper, we know that at most half it's a non-negative function. It's either positive or zeros, and the weight of the positive guys is at most half. So you can, if G is proper, then without loss of generality, let's order the vertices. Order vertices such that we have the following. G1 is the largest value, then G2, and so on up to GS, which is greater than, these are the non-negative guys, which is greater than 0. And from then onwards, it is gs plus 1. All of them are all the way up to gn. They are all. And furthermore, that phi of the set 1, 2, 3 up to s is less than half. We can do this sort of ordering. Okay. Without loss of generality, we'll order the vertices such that the first s guys are the largest guys, are the ones greater than 0. And in fact, they are in descending order. They are in non-increasing order. And then from s plus 1 onwards, it's all the 0 elements. So now let's consider this following quantity. Consider the way we're going to prove is consider the quantity summation I less than j phi I wij f square I minus f square j. This is a quantity star which you're going to consider. What is this quantity? So if you look at the things on the line, this is G1, G2, sorry, not F, G, G3, all the way up to Gn. What is this? And there are edges. Notice that there are edges going across like this with weights, and the weight of the edges is pi I wij. What we are writing down is for every edge, we are writing out the difference between gi square and gj square and multiplied by the weight of that edge. That's what we are doing. We're just summing over all the edges of the difference between gi square and gj square summed over across all the edges. So yeah, I want to look at this quantity. So this quantity just by this one. So this can be written as I less than j phi I wij. Because it's gi square minus gj square, I can write it as a telescopic sum. I can write it as k going from I to j minus 1 g square k minus g square k plus 1. And that sum will just come out to g square I minus g square j. This, now let's reverse the order of quantifiers. So this I want to write this first. So k equals 1 to s. These are the only terms that matter here. G square k minus g square k plus 1. What will be the, if I reverse the order of summation, what will this be multiplied by? So look at, let's take a particular k and a k plus 1 in this. So this is gk and gk plus 1. How many times does gk and gk plus 1 appear in the summation? It appears whenever there's an edge going from the left of gk to the right of gk plus 1. Only then g square k minus g square k plus 1 appears in the summation. Whenever there's an edge from the left of from 1 to k to this one, only then you get a sum. So in fact, this is exactly the weight of the edges that cross this particular cut. Is it edges going from gk to gk plus 1? You're looking at those edges, and it is the total weight of the edges that cross this cut. If an edge completely lies it's completely within 1 and k, it will not contribute to this sum. It will not contribute to this sum at all. If it's completely to this side, it will not contribute. Only when the edge is crossing between this one. So I want to claim this is exactly dou of one, 2 up to k. It's exactly the sum of the edges crossing this particular cut. Okay. But this quantity is greater than or equal to summation k equals 1 to s g square k minus g square k plus 1 phi times pi of 1 to up to k. Because this is the definition of phi. Phi is the minimum of all this. Therefore, any cut, the dough of that set will always be larger than pi of that set. So what is this? So this is just phi times summation k going from 1 to s g square k minus g square k plus 1 pi of 1 to k. Let's write this a little more carefully. I want to write this just as k equals 1 to s. Just write g square k. What's the coefficient of g square k? Let's collect terms. Just this is just g square 1 into something plus g square 2 into something plus g square 3 into something. What is g square k? G square k appears twice in the summation. Once for k and once for k minus 1. And it appears with pi 1 to k and pi 1 to k minus 1. So in fact, once with this one, so this will exactly be just the pi k. But what is this? This is exactly phi of gg. So the star quantity, we have lower bounded it by the norm of the proper function g. Let's also go and look at it in the upper. Let's upper bound it. So star was once again summation I less than j pi I wij g square I minus g square j. Now we have done. There's only one thing you can sort of do. This is Cauchy-Schwarz when you're doing this sort of thing. So this I'm going to write as summation I less than j square root pi I wij gi minus gj, this whole thing into once again square root pi I wij gi plus gj. Cauchy-Schwarz will give you that this is less than what? This is less than I less than j. I less than j pi I wij gi minus gj. By the way, why did I want to do this? I wanted to get gi minus gj the whole square. I don't know how to get it from g square I minus gj square. So one way of getting it is via Cauchy-Schwarz. So this is this quantity, this to the power half times summation I less than j pi I wij gi plus gj whole square, the whole to the power half. I want to rewrite all of this in terms of the Laplacian. There are only two quantities which I can write is GLG and GG pi. These are the two things. These are the two inner products. I want to write it down. So I written it this way. The first is a term which we know. The first is already GLG pi to the power half. That was the first term. What about the second term? It's not exactly what we want. This is not one of the terms we had written, but let's try to convert it to the Laplacian. So this is I less than j pi I wij. I can write it as 2 g square I plus g square j minus gi minus gj whole square, and then the whole of this the power half. I just written a plus b square as 2a square plus b square minus a minus b square. Once again, so this is GLG pi to the half. What is this? This I want to claim this is exactly twice summation pi I g square I. these two sums will turn out to be this minus summation I less than j phi I wij which what is this? This is just 2 gg pi minus gh. What have we shown? We have shown star is less than or equal to square root of glg pi times 2 gg pi minus so this is say 2 and this was 1. If you put them together, we have p of gg pi is less than or equal to square root glg pi into 2 that is p is less than or equal to square root rho into 2 minus. That finishes it.
Okay. Can you go to the point where we did the Cauchy sorts?
Yeah. I'm just using summation AB is less than or equal to summation A square, summation B square, the whole under square. Yeah.
Right. And then in the line where you had this 2gi square plus gj square, and then how did we get to the next line with just summation over I pi g square?
This is summation. So let's look at this. This is summation over every edge of 2g square I plus 2g square j.
Yeah.
Therefore, every edge is going. So look at a particular I. The particular I is going to be sub pi wij for all the weights going out of it, and that sums to 1. So therefore, you'll just exactly get this.
Yeah.
This is just stating that the sum of the edges is like the what is it? This. Okay. The sum of the edges is like the twice the degree. Yeah, this is exactly the same thing, but then the weighted version of it.
Yeah.
Sum of the edges is the sum of, sorry, if you count sum all the edges, that is exactly twice half the degree. Twice the degree of the, or half the degree of this one.
Sum of degrees twice of edges.
Yeah, sum of degrees is twice of edges. This is exactly the same thing going on over here. Okay, so this does our proof. This completes the Cheeger inequalities, but I want to say actually we have done a little more. So the proof actually the proof was constructive. You gave me the second eigenvector, and then it actually showed to you it constructed a small set. And not only the small set, it in fact only the set it showed was the proof. The proof actually demonstrated that there is a set. Proof demonstrated that there is a set yes of the form 1, 2, 3 up to some I, where I is less than or equal to s, such that phi s is less than or equal to square root 2 lambda 2. In fact, it told you that one of these sets itself, because this was the only sets for which we actually applied. If you recall, in this part of the proof, in the best part of the proof, in this part of the proof, these are the only sets for which we needed this conductance. That pi of ik is larger than this. So as one of these sets we already showed is already a small this one. We didn't have to go over all sets. One of these sets is all that we cared for. So we showed this. So this in fact gives us this following thing, which is called the Feedless algorithm. It tells you the hello.
Yeah. Can you?
When did you guys lose me? When did it get cut?
You mentioned the name of some algorithm.
Okay, fair enough. Okay, not too long ago. Just let me connect my. The network might be flaky because of. I don't know how because of the storm outside. Storm. This one is connected. Sorry about this. And the vector f says that f is orthogonal to the all ones in the phi norm, and f LF phi is say less than or equal to alpha times FF phi. Then this algorithm will output a cut S P minus S such that phi S is less than half and PFS is less than or equal to square root alpha. And more or less, this should be clear what this algorithm is going to do. This algorithm is the fairly following simple algorithm. It's just going to first, if phi of I such that phi is greater than 0, is greater than or equal to half, then flip f, replace f with minus f, order the vertices, such that f1 is greater than or equal to f2 is greater than or equal to fs, is greater than 0 equals fs plus is greater than or equal to fs plus 1, and so on up to greater than or equal to fn. So you order them on either side of so you basically order them on either side of 0. And we have mentioned, taken care that this side is less than half the weight. And then just compute phi of 1 to I for I in 1 to S and output the cut with the least conductance. So instead of searching over all an exponentially large, it just says it searches just over these S possible cuts. These are what are called threshold cuts, and says one of them is going to give you the minimum. One of them is a candidate small cut. And that's what the proof has already shown to us. Okay. Any questions so far before I do some concluding remarks on the Cheeger inequalities? It's a very quiet class. It's raging outside and you guys are very quiet here. Okay, so let's go to, we did Cheeger inequalities. I want to ask tightness of Cheeger inequality. So we showed upper and lower bounds. In particular, Cheeger inequalities was this statement: is less than or equal to square root 2 lambda 2 by 2. These were what we called the Cheeger inequalities. And I want to ask, are these inequalities tight, or can you tighten them? So forget about the orders. I want to show there are examples for graphs for which this inequality is tight. There are examples for graphs for which this inequality is tight. So you can't improve either direction. That is, what we have proven is more or less the best we can sort of imagine. So let's look at the direction phi g greater than or equal to lambda 2 by 2. The example for this, the tight example for this is the hypercube. So hypercube, what was lambda 2? So recall hypercube is a Cayley graph. So its eigenvalues are just going to be, eigenvalues of the adjacency matrix is just going to be the characters are going to be the eigenvectors, and the eigenvalues are just going to be the eigenvalue corresponding to a character. Take that character and sum it over the generators. It's not hard to see if you do this that what is lambda 2? If you stare at this, you can actually show that the eigenvectors corresponding to second smallest eigenvalue are the characters corresponding to singleton sets. What do I mean by that? So there are these characters. A character corresponding to a set S was a function from V to R, so that phi S of x1, x2, xn was mapped to summation -1 to the power summation xi I in S. And the singleton characters are when these are exactly chi of just I. So chi of S of 0, 1 to the n to the R is the thing that maps x1, x2, xn to just -1 to the power xi.
Prahladh, is the summation extra in the chi-s definition? The summation that is not in the exponent?
Sorry, so there's no that summation. It's just -1 to the power summation xi I in S. You're right. Okay, so these are the singleton characters, and you can check that their eigenvalue is actually the second eigenvalue in the Laplacian world is 2 by n. If the Boolean hypercube is, if this is the Cayley graph corresponding to 0, 1, n, and the generators being E1, E2, En. These So for lambda 2 is 2 by n. And what is a cut which is really small? What I want to tell you is, what are the, so lambda 2 is 2 by n. And I want to tell you, what are the really tiny cuts in this graph?
They're just like slice the cube in half. That would be the smallest, right?
Small in half in the sense you take a particular coordinate I, put everything xi equals 0 on one side and xi equal. Yeah, exactly. These are called what are called, these happen to be the smallest cuts. These are what are called the dictator cuts. Basically, one variable is deciding, it's the dictator because that variable is deciding which side of the cut it is going. So the cut is basically S is set of all. So yes, I. So I'll take any I in n, and Si is the cut. It's a set of all x in 0, 1 to the n, such that xi is 0. And the cut. And what's the value of this cut? How many edges are cut by this? Exactly, you have taken the Boolean hypercube and you have constructed this cut, basically. The dictator cut, the cut that slices the Boolean hypercube. So what out of
half of all the vertices?
No. That is the vertices. The cut value. So phi of Si. What is phi of Si? Phi of Si is the total number of edges crossing the cut by the total number of edges leaving the vertices in the cut. Now notice that out of every vertex, only 1/n of the edges actually cross the cut. Every other thing goes within the cut. Therefore, this number will be 1 over n. And that gives you the tightness of this direction. This direction is actually tight. In fact, it's tight up to the constant. The hypercube exhibits phi g is greater than or equal to lambda 2 by 2. Second eigenvalue is 2 by n. And the minimum cut is actually the dictator cuts. So the second example which I want to talk about is the other direction. Phi g is less than or equal to square root 2 lambda 2. And here the tight example happens to be the cycle. That is Cn, which is what? Which is the Cayley graph on Z of Z and Z, with generators being +1 and -2. Okay. What's the cut for this? Suppose S is a connected set of vertices. The connected set of vertices. What is PS for this graph? How many edges? Suppose S is a connected set of vertices. How many edges?
2 by S.
Get out. 2 by 2 size.
1 by S.
1 by S. Exactly, it's 1 by S because the number of edges, potential edges, are two times the size of the vertices, out of which only 2 actually cross the cut. So it's basically this example. S is this guy. Therefore, the only guys crossing the cut are this particular edge and this particular edge. All the other edges are within the cut. And you can check that if S was has disconnected components, it's going to be even. This is the worst. The kind of connected case is this one. Anyway, this is a cut. And we already saw that once again, it's a Cayley graph, lambda 2 for this graph. You can actually compute it. I'm not going to. This one, lambda 2 for this graph happens to be equal to 2 into 1 minus cos 2 pi by n. This is something you can just pull out of the Cayley graph. You can get to the characters, from the characters, you can get this. And this is something, if you, for small values of n, this is like theta 1 by n square. If you look at the cosine expansion, the Taylor expansion for cosine, this is theta 1 by n square. Therefore, you have this quadratic gap between what's the smallest cut? The smallest cut, therefore, phi of g is something like P of G is something like 2 by n, roughly. You want to make this as small as possible, which is the S that you take, which is a cut which you're going to take so that most edges remain. You choose you choose a path of length n by 2. Most of the edges are going inside, just 2 go outside. So this is exactly if you can show that this is the min cut of the cut with the sparsest, this one. And on the other hand, lambda 2 is 1 by n square. And this gives you the other direction. So the Cheeger inequalities are tight in both directions of the questions. Shubhada, did you ask a question or?
No.
Okay.
Yeah. In the denominator of phi is, I mean, if you have a path of length s, then in like the number of edges incident on it would be like s, or I guess s plus 1 maybe, but how is it 2s?
No, this is not the number of edges. It is the denominator is not the number of edges. The denominator is how many edges. You have a set of size, yes. You are asking
the numerator summation of degree of everyone.
Summation of the degree. It's pi summation pi I.
Okay. Yeah.
These are all the edges that could potentially leave this. How many of them are actually leaving it? They are potentially 2 over s. It so happens so many of them just collide within each other and do. That's how it was defined to be. Okay. So these two examples show you the tightness of both the two extremes. The Cheeger inequalities cannot be sort of tightened. You do have a quadratic loss for the cycle. You do have this in this direction. So there are examples in which both of them are tight. Now you could ask one more thing, which before I wrap up the entire discussion on Cheeger, is the tightness of the Feedless algorithm. What did we claim? Feedless algorithm produced a set yes, such that P of S was less than or equal to 2 lambda 2. This is what Feedless algorithm produced. But we know but P of S is always greater than or equal to lambda 2 by 2. The question is, suppose actually you could ask the question, suppose it was a hypercube setting in which actually P of S there was a very small cut which was close to this. Now, does Feedless algorithm give me a cut which is close to 2 square root lambda 2, or actually gives me lambda 2 by 2? So I gave the hypercube as the input graph to Feedless algorithm. You know, it is the direction of the tightness is, there's a cut of size very small. There's a cut of size 1 over n. But is Feedless algorithm going to give me a cut of size 1 over n, or more like 1 over square root n? That's a question you can ask. I want to claim, unfortunately, Feedless algorithm is going to give me a thing only of 1 over square root n. Even if the cut size is 1 over n, Feedless algorithm guarantees 1 over square root lambda 2. And in this case, for example, what did we see? We saw that what did we see? We saw that which were the second eigenvectors? The second eigenvectors were what were the second eigenvectors? The second eigenvectors corresponded to characters of singleton sets. In particular, it corresponded to these guys, chi of I going from 0, 1, n to R, in which x1 to xn was being mapped to -1 to the power xi. And all of them had second eigenvalue 2 over n. So I could have actually given, so who knew that I should give one of the dictator. If I certainly give the dictator cuts, if I give these as the eigenvalue to eigenvector to Feedless algorithm, it is going to give me the dictator cuts. But notice that this guy also, chi, which is summation chi I, that's also a second eigenvector. It's something in the linear combination of second eigenvectors is also a second eigenvector over all I in n. This is a function mapping. Let's look at what this function does. This is mapping x1 to xn to summation minus 1 to the power xi I in n. So what is this quantity minus 1 to the power xi? If you notice, this is exactly, this is n minus 2 times the Hamming weight of x. It's whenever x is 0, this is 1, 1, 1. Whenever x is 1, it gives you a minus 1. Therefore, this is exactly n minus 2 times the Hamming weight of x. So if you look at this, if I'm going to draw this cut hypercube this way, this is the Hamming weight 1, guys, Hamming weight 0, guys, Hamming weight 2, guys, Hamming weight n by 2, guys, Hamming weight n, guys. I'm writing down the hypercube in increasing order of Hamming weight. So this is also a second eigenvector. So if Fiedler had fed this as an input, it is going to find a set of vertices which it's going to find a threshold cut. And what's a threshold cut? A threshold cut is basically something between one Hamming weight to the next Hamming weight. It's basically this. It's going to put all things below a particular I on one level, all things above a particular I, because it's going to line up the vertices according to their eigenvector value and put everything on one side to everything with this one on one side, this one. So it's basically the threshold cut exactly is one of these is you choose a particular Hamming weight and choose everything below it on one side, everything above it on the other side, which is the cut which is going to have the this one, the worst possible thing. It will be the minimum cut, the min cut this way will be what is called the majority cut. That is this cut. If you want to minimize this one, you can check out the value, and its value will be actually be order 1 over square root of theta. In fact, theta 1 over square root of, and that has the quadratic clause. For example, the cut at the bottom is going to, okay.
Prahladh, so
yeah,
just something tangential maybe. I mean, the terms that I'm seeing here are something that were of importance in the Boolean functions course, like dictator and majority. Is there some Fourier analytic importance here for this? Like
it is no. These the many things this will happen, that is, you will be working with dictators, you will conflate them with majority, and you'll have to differentiate between the two, whether you are working with a dictator or whether you're working with a majority, and you won't be able to tell apart. And these are some ways of telling them apart, and these come very naturally. It's because of this Boolean function analysis we study dictators and majority. It's not the other way around. It's because these cuts are nice. The dictator cuts, the majority cuts are nice cuts. Those form nice functions over there, and we study them over there. Okay. This took much longer than what I thought, but is Cheeger inequalities and this one fine now? So we proved both the easy direction, hard direction. We gave upper bound and lower bound. We show that if the small second eigenvalue is small, then the hard direction shows there is also a cut which exhibits small conductance. If there's a set with small conductance, I can from it pull out and show that the second eigenvalue also has to be small. The Cheeger gives both directions, but there's a quadratic loss in this, and that quadratic loss is necessary. In such a relation, you can't improve it. There are graphs which witness tightness on both ends, so you can't improve this any further. Any questions? So then we'll wrap up this in the remaining 20. Yeah, so that.
So are there some robustness relations that if Cheeger is tight on the left-hand side versus the right-hand side, you can say something about the structure of the graph?
For Cheeger itself, I use a robust statement. You want further robustness. You want to say if Cheeger is It's closer to this side.
Yeah.
Can you tell something about what do you want? What sort of
So
statements do you?
like in this, like you gave an example of the cycle versus the Hamming cube for the
Yes.
loss. So can you
Yeah.
say something like, I don't know, maybe the spectrum of the graph looks more like a cycle if it is. I don't really know what statement to look for, but structurally some kind of structural similarity between the graphs, maybe.
I don't know. I don't know. I haven't seen such a statement. I don't know. I don't know.
Okay. Okay.
What you could do is potentially keep breaking the graph. That is one thing you could do is you give me the second eigenvalue, I could break the graph, take the cut, break it. Now look at the two new cuts. And does this decomposition give you something about it? I don't know. It could give you some meaningful. You keep breaking the graph into parts based on, you give me a second eigenvector, that gives you a cut. Now you break the graph into two parts. You have two graphs. You look at their second eigenvalue. Once again, break the cut. This one, whether this gives you some, it might give you a structural decomposition of the graph.
Okay.
It possibly gives you a decomposition in which the number of edges that you are throwing out eventually in this hierarchical decomposition is very small, not too large, but I'm not sure. Yeah.
Okay.
I don't know. So our next topic within this one, we're going to briefly talk about what are called expander graphs. So in general, so particular here, I'll be working mostly with d-regular graphs. So the statements I prove d-regular graphs, therefore the random walk matrix is a very nice matrix in this case setting. So we'll work with d-regular graphs and we'll say a particular G, VE, it's a d-regular graph, is a gamma spectral expander if lambda is G, which is, let me not call it lambda of G, let me write it as the second, if omega of G, which was the max of omega 2 of G and omega n of G, because the maximum of these two quantities, this omega of G is less than or equal to 1 minus gamma. So let me state what is happening. So we had this graph, we had this eigenvalues of the random walk matrix. We saw that omega 1 was equal to 1. Omega 2, if the graph is connected, is bounded away from 1. And if the graph was non-bipartite, omega n was bounded away from minus 1. This is 1, and this is minus 1. And this quantity is what I'm going to call the spectral gap, the max of these two quantities. The min of these two quantities is the spectral gap. And that is what is gamma. So this is usually either said gamma spectral expander or spectral, or it is said the spectral gap is gamma, or it's called just a gamma expander. These are various terms for it. So people might have called it, you might have seen literature in which this is actually called omega expander, not gamma expander. We refer to it by this value rather than by this gap value. But it's more convenient. For that instance, to look at the complete graph, omega is 0. Omega is 0. And therefore, then you will be talking of the fact that it is a 0 spectral expander, whereas actually it's a best spectral expander. Therefore, we would rather talk in terms of the the spectral gap rather than the spectral gap for the complete graph is 1. Therefore, it's a 1 spectral expander. It's the best spectral expansion that you can have. So whenever you talk about a graph and its spectral expansion, we'll talk with respect to spectral gap. A spectral gap is this gap. It's this gap. So I should possibly magnify this, write this a little better. So that was this one. This was 1. This was -1. Omega 1 was sitting here. Let's take this is 0, say. Omega 2 is over here. Say omega minus omega n is over here. So the minimum of these two, the min of these two is what is called the spectral gap. And the larger this quantity, we're going to say the graph expands better. Notice for the graphs that we saw, hypercube, cycle and all, these are really tiny quantities. These are like 2 by n, or which is 2 by log n for the hypercube. If the number of vertices is 2 per n, in terms of the number of vertices, it's 2 by log n. 2 by log n. For the cycle, it's even worse. It's like 1 by n square, the spectral gap. But what we're going to talk about is gamma. So we'll say a family of graphs. So a family of deregular graphs Gn, n going from 1 to infinity, is a gamma spectral expander if firstly the graphs are all deregular, all of the families in the graph, it's a growing family. For each n, you get larger and larger vertices, and omega of Gn for all is less than or equal to 1 minus gamma for all n for all n. So both the second eigenvalue and the largest eigenvalue, both are separated away from 1 sufficiently, 1 and -1. Then we call this to be a value. And this gamma is a constant. This gamma is this is a fixed constant. Gamma is some fixed constant. It's like θ1. Of course, the definition can make sense even if it's not a constant, but we will talk about constant, guys, and we'll soon see why this constant, why I care bothering about constants. Is the definition clear? So an expander is just basically a family of graphs, all of which, in which the spectral gap is at least a constant, a fixed constant. So this growing family. Notice the hypercubes cycles are grossly violated. The gap keeps on shrinking as the graph becomes larger and larger and larger. That's not the family of graphs I'm looking for. I'm looking for a family of graphs where the constant is a fixed constant, irrespective, even if the graph size keeps going larger and larger. Okay. Why do I care about this? Why is this an interesting property? Firstly, there are two things we need to ask. Why do such graphs exist? Do such graphs exist? Is this a meaningful definition, or is it a vacuously true? It's a vacuous definition. And secondly, if such graphs exist, are they useful to us in any sense of the word? We will, in the next 10 minutes in this lecture, and possibly rather 20 minutes of the next lecture, we will spend time trying to answer both these questions. Varun, yeah.
So what this definition, what does it say about the conductance of such graphs?
So it says the conductance of every cut, they cannot be a cut with this too small, because the conductance of a graph is between lambda 2 and square root 2 lambda 2. Both of these are constant. So what does it tell you about the conductance? What does it tell you about the conductance? It can tell you that the conductance of this graph is not, it does not give you a graph which has conductance arbitrarily small. That's all it tells you. Okay. These graphs are such that no matter which cut you put, there will be a good number of edges. In fact, we will see this. What does this tell you? In terms of Cheeger, what does it tell you? No matter which cut you take me, there will be a good number of edges that actually cross the cut.
Okay. And this is, I mean,
So
and you get
in
this
that sense,
even
this is
as
why
you
it's
grow.
called, this is an, you get it as, no, it's a fixed constant. It's the same constant because it's always this fraction of the edges go out and the fraction is a constant fraction. And this is why these graphs are edge expanders. That is, take any set, fair number of edges actually go out of the cut. They don't stay in the cut. This is a family of graphs for which no matter which cut, so basically the conductor Cheeger is going to tell you, if I draw this graph, yes, a large number, a constant fraction of the edges actually are going to get out. And this is quite a remarkable property of this graph. That is, take any vertex, it is an edge expander. Cheeger inequalities tell you, Cheeger inequalities give you that every cut in a gamma spectral expander has a constant fraction of edges going out. Going out rather than going in. Okay. And this is the reason why these graphs are hard to draw. That is, there is graphs which are nice to draw are graphs in which that you put the vertices as that once if you cut it this way, once you draw the graphs nicely, they will be cut such that very few edges cross. But this is a thing in which no matter which set you choose, there won't be a small cut. There won't be a nice cut at all. Every cut is going to have lot of edges. So in that sense, this graph is an extremely well-connected graph. It is in some sense like the complete graph. The complete graph is all the cuts are, every cut is more or less close to one. Most of the edges are going out. There are very few edges going in, staying in. Most edges actually leave the thing. And this car also has the same thing. It's not most, but it's a constant fraction of them actually leave out. It's unlike the hypercube or cycle in which eventually there will be cuts which are really, really tiny. Most edges stay inside this one. Whereas this here, a constant fraction of the edges actually go out. This is related to edge expansion. The Cheeger inequalities tell you why this one, but Cheeger inequalities required only lambda 2 to be separated from 1. We didn't care if lambda n is separated from 1. What we'll show is there's another notion of expansion, which is called vertex expansion. And that is implied by lambda n being this one. So let's go to, so this is, by the way, this is gamma. Here I had to set, gamma is some number between 0 and 1. Gamma is a fixed constant between 0 and 1. That's a spectral.
So this notion is, this is covering both edge expansion and vertex expansion. Yeah?
No, if lambda 2 is bounded away from 1, that covers edge expansion. That's what Cheeger inequalities is telling you. Now, if also lambda n is bounded away from 1, it will give you vertex expansion. Now, because the way I defined expansion, I said both are bounded away, it gives you both edge and vertex. Yeah. But if you just cared about edge expansion, you only care about lambda 2. But what we will see more interestingly is vertex expansion. So let me say, this is a combinatorial notion. So vertex expansion. So G equals BE. Once again, it's a deregular graph. We'll work with only deregular graphs while talking about this. Deregular graph is the KA vertex expander for some K which is, K is a number between 1 and V, and A is a number greater than 1. Greater than or equal. Greater than 1. If for all sets of vertices of size, this one, such that if mod S is less than or equal to K, for all not too large, take this one, then you have that the neighborhood of S, which is what? Which is a set of all J in V such that there exists a I in S such that Ij is an edge. like this. Okay. The neighborhood of S is at least A times the size of S. That means you take any set of vertices. If the set of vertices is not too large, certainly it can't be all the vertices, because if you take all the vertices, its neighborhood doesn't grow by a factor larger than 1. Take any set which is not larger than K, its neighborhood, the set of vertices it is adjacent to, is at least a factor A larger than itself. Okay, so what are we claiming here? So I take a graph, I take any set S and look at its neighborhood. So it could be N of S there. The claim is N of S is at least A factor larger than it. N of S can include S, it need not include S. By the way, N of S is a set of all vertices that are adjacent to some vertex in S. Okay. Sometimes people include also N plus S, which is S union N of S. But right now we'll talk only of N of S. S union N of S is things which are at least one step away, which are at most one step away from S. This is what N plus S means. N of S is which are things which are exactly one step away from S. Okay. Is a definition of vertex expansion clear? This is what I mean by vertex expander. It's a KA vertex expander. This is true. And the first nice lemma we'll see. Informally, it will say spectral expansion implies vertex expansion. And before I state the lemma, we'll actually see the proof of this and then fill out what quantitatively what spectral expansion will imply. So I'm going to basically say if G is if GVE is has spectral gap gamma, which is 1 minus omega, then G is a alpha n some vertex expander. And we'll fill this for every alpha in 0 to 1. Alpha, you take it to be 1/3. Every set of size at most 1/3. We'll say 1/3 the number of vertices expands by some factor. We'll say alpha to be 1/10. We'll give a particular picture. And the proof is going to just use the expander mixing lemma. So recall the expander mixing lemma stated that FG phi minus expectation F according to phi, expectation G. Let me write this in very succinct form. The expander mixing lemma said this: mu of F into mu of G. This is less than or equal to lambda times, not lambda, omega times sigma F, sigma G, where mu F is defined to be expectation of F of I coming from phi, and sigma F is variance phi coming from phi of F of I, which is the same thing as this is nothing but expected value of F square of I coming from phi minus we proved the expander mixing lemma first. We'll use the expander mixing lemma. In fact, we'll see several nice applications of expander lemma in the next one. So how are we going to do it? So let S be the subset of vertices. So, mod S is something less than equal to alpha n. And let T be the neighborhood of S. Okay. So so I'm going to define F to be the indicator function of S and G to be the indicator function of, actually, let me not take P. So let me set P to be the vertex set minus n of S, and G to be the indicator function of 1 of T. What is FG phi in this case?
Zero.
Zero. This is 0. Therefore, what do we have? We have that. So let's call this. Should I call this? Should I not use alpha for this? Let me not use alpha for this. Let me use rho for this. And let size of S be equal to alpha n. So alpha is some number less than rho, and size of T be size of, and let n of S be size of n of S be. Let's do this carefully. So let's let size of S be equal to alpha n, and size of n of S be beta n. Why am I writing capital N? Alpha n. No idea why I've been writing capital N altogether. Beta n. Therefore, size of P is 1 minus beta. So let's just apply EML. What do we have? We have F G phi minus. So for EML, we have this to be 0. Let's look at all the quantities of this one. What is mu of F? What's the expected value of F? This is expected value of 1s. When I pick I from phi. This is a uniform distribution because it's deregulates the uniform distribution. What will this be?
Phi.
Huh? So this will be pi s, which is
alpha n.
exactly, yeah, pi s, which is alpha. Actually, I could have just kept pi s. I don't know. Okay, pi s. Huh? Okay, let's just keep it as pi s. Why bring in new notation? This is pi of s. Mu of g, the same thing is pi of t. Yeah, no, I know why I wanted to become. So this is alpha, and this is 1 minus beta. And what is sigma f? Sigma f is the variance of a Boolean random variable that is exactly alpha into 1 minus alpha. Of a Boolean random variable, the variance will be the mean into this one. Similarly, sigma g will be beta into 1 minus beta. So just applying EML, we'll get that alpha into 1 minus beta is less than or equal to omega times square root alpha 1 minus alpha beta 1 minus beta, which is the same. Now I'll square both sides. I'll get alpha into 1 minus beta is less than or equal to omega into 1 minus alpha into beta. I want to put a bound on beta size, sorry, omega square. So I want to say beta into omega square 1 minus alpha plus alpha is greater than or equal to alpha. Therefore, beta is a number which is always larger than alpha by omega square 1 minus alpha plus alpha. And this number is always larger than alpha by omega square 1 minus rho plus rho, where since alpha is a quantity less than or equal to rho all the time. The easier way to see it would be the other, had I written it, this is equal to alpha by alpha into 1 minus omega square plus omega square, and hence that this is greater than this quantity. All I'm claiming is, so what has happened over here? So if you take, what have we proved? Just it's a vanilla application of the expander mixing lemma. Modulo the calculations, it says the size of, so we had this set. We had S. Then we looked at the neighborhood of S, and then we constructed T, which was the complement of the neighborhood of S. And there are no edges going between S and T, the way we define them. We show that beta, the neighborhood of this, should be at least this size. Now notice, this is exactly the size of S. And this is a, what is this? This is a quantity I want to say, which is larger than 1, smaller than 1. Because it's rho plus 1 minus rho, it's 1. Rho plus omega square, if omega is bounded away from 1, this is a number less than 1. Therefore, as an A, this, so in other words, what we get, hence G is a rho n 1 by omega square 1 minus rho plus rho expander. For all rho n 0, 0. So if it has a constant expansion gap, then this factor is also constant. If the spectral gap, if the omega was a constant, is bounded away from 1, this number is also a constant larger than 1, strictly larger than 1. Of course, this number could go very close to this one. So this tells you, this is basically telling you spectral expansion. This is what I wanted to fill here. This is like 1 by omega square 1 minus rho plus rho. Okay. Is this clear? I might go over some of them. I possibly went a little bit fast today. This is just a vanilla application of the expander mixing lemma. There's nothing that happened over here. Expander mixing lemma plus the definition of spectral expansion tells you every spectral expander is a vertex expander. And we'll see some amazing properties of vertex expanders next lecture. Why are vertex expanders nice objects? We'll also see why are spectral expanders nice objects. We'll see this one there. And of course, we need to answer the question, do such objects exist? Right now, it's just a definition. If there's no such, I'll give you explicit constructions of such objects. We'll not just give you explicit, we'll give you super explicit, and we'll define what super explicit means in the graph size will be exponentially large, but yet you will be able to give me a very explicit construction. We'll see both of this on next lecture on Wednesday. So by the way, I might postpone the Wednesday lecture to Friday. I'm not sure. Wednesday evening, afternoon, I'm giving a talk. So if I'm not yet prepared for the talk, I might cancel the morning lecture and postpone it to Friday. Okay. That's any questions so far?
The definitions of like vertex expander, was it only for deregular graphs? Like,
yeah, so you could define it for non-things also, but when an application when you use an expander graph, you use an application only where it's deregular. So it's nicer. So by the way, all the theorems which you have proved are true for every statement I have proved is actually true for in general also. You could have taken anything which has a spectral gap, doesn't have to be deregular. All the theorem, nowhere in the theorems I use it. But it's nicer if the graphs are deregular, and we'll give explicit constructions where actually the graphs are deregular. So the stationary distribution will be the uniform distribution on the vertices. Okay. And there will be places where for the applications we actually want the stationary distribution to be the uniform distribution, not some other distribution. The theorems I write on will be true for any expander. They will be true for any of these things, but So later on, applications of expanders, we will require them to be the uniform distribution. Okay. Any other questions? Okay then.